Alright, welcome to AP Physics 1, Unit 6, Ultimate Guide. In the last unit we learned about rotational motion, and in this unit we applied it to energy and momentum. And as you see as you work through this unit, you will see that a lot of the same ideas from linear motion when we talk about energy and momentum are very similar ideas when we apply it to rotation. We just use a little bit of different variables, and sometimes you have to factor in some other components, but a lot of it is the same principles, which hopefully should feel familiar. So we have all the timestamps and descriptions, so feel free to jump around as you need. We get into a lot of fun examples, especially in the later half of units, so make sure you stick around for those. So yeah, let's get started. So if we have an object, let's say like a sphere, and it's rotating around on some axis, and it's not moving linearly, then all of the kinetic energy, the total kinetic energy, is just this rotational energy. And we can think of that as every little particle, every little atom in this ball is rotating, so it has some linear velocity. And when we sum up all of these individual linear velocities, since it's moving around, we can describe the motion for the kinetic energy in terms of this equation. So let's see how we derive this equation. So let's say we have the kinetic energy equals the 1/2 m velocity squared. This is the typical kinetic energy of linear motion. This will be the tangential velocity. And we learned previously that the velocity can be related to the angular velocity using r times the angular velocity. Okay, so if we go ahead and we substitute that in, we'll have k equals 1/2 m r omega squared. And so if we distribute that square in, we get 1/2 mr squared omega squared. And you may be noticing that this mr squared right here simply just equals I. So we will get k equals 1/2 the rotational inertia times the angular velocity squared. And that's what we have right here. Okay, so let's look at an example using this equation. So we have Bob spins a 0.1 kilogram top on the table. It rotates 100 times in 25 seconds. The top has a radius of 2 centimeters and can be treated as a solid disk with the rotational inertia 1/2 mr squared. Okay, so what is the kinetic energy of the top? So let's start how we'd always start and list out our variables. So we have the mass, which is 0.1 kilograms. Okay, we have 100 revolutions, and for a time of 25 seconds. We have a radius of 2 centimeters, which we'll want to get that in meters, so that's just 0.02 meters. And then we were told what this rotational inertia, rotational inertia can be described as 1/2 mr squared. Okay, so if we want to find the kinetic energy, we're going to need the rotational inertia and this angular velocity. And so this is what our rotational inertia is. We have the mass and we have the radius, but we need to get this angular velocity. And so we can figure that out using these variables here. So we want to find this, and this is going to be in radians per second. And so we have that it did 100 revolutions. Okay, and we can create this sort of table with conversion. So we know in 1 revolution, that's 2 pi radians. 2 pi is around a circle. And so that gives us our radians because the revolutions cancel, and so we get 200 pi radians. Okay, and so now we just need to get the angular velocity, which we know is radians per second, and we have the time. So we can simply plug those values in as 200 pi radians in 25 seconds. And so that equals 8 pi radians per second. And so now we have all of the variables that we would need to solve this. So we can go ahead and plug them in. We have our k, which equals 1/2, and then the I is its own 1/2 mr squared times this angular velocity squared. So if we go ahead and plug in our values, we can combine these fractions to get 1/4. The mass, which is 0.1, the radius is 0.02 meters, because we need it in meters, and our angular velocity is 8 pi squared. And so our kinetic energy, if we plug this all in, will be 0.0063 joules. Okay? And so that's how we can find rotational kinetic energy. The work equals the torque times the change in theta. And so how did we get this? Well, if we think about what work means, or what we talked about work in linear motion, is the work is just the force times the distance. But when we have a rotating object, let's say it's like rotating around some point, this distance equals the angular or the arc length around here. So we can actually say this work equals the force times, we'll call the arc length S, right? And so what does S equal? Well, we learned previously that S equals the radius times the change in the angle. So if we plug that in, we get force times the radius times the change in theta, and we know that the force times radius is just the torque. So that's how we can derive this equation, and so that's what we said that was. So we can use this to solve problems for work of rotating systems, and we'll see how we do that right here. So a solid disk with a rotational inertia of 2 kilograms meters squared and a radius of 2 meters initially at rest. A constant force of 4 newtons applied tangentially to the disk, causing it to rotate 6 radians. How much work is done, and what is the disk's final angular velocity? Okay, so we have a lot of things going on, so let's start by just simply listing what we know. So we know I, the rotational inertia, is just 2 kilograms meters squared. We know the radius is 2 meters, and we know it says it's initially at rest, which will come in, and we can go ahead and write that now actually. We have our angular motion, or angular velocity is initially 0 because it's at rest. Okay? A constant force is applied equal to 4 newtons tangentially to the disk and cause it to rotate 6 radians. So the change in angle is 6 radians. So we want to know how much work is done and what is this final angular velocity. Okay, so let's kind of draw out quickly what we have here. So we have some disk that's rotating or starts at rest, and a force is applied tangentially and it causes it to rotate. So we want to find what is that work that's done and the final angular velocity. So let's start with work, because we'll actually use work to find the final angular velocity. So as we learned before, we know the work is the torque times the change in theta. And so we know also that torque is force times radius, and then we have our change in theta. And so we know the force, we know the radius, and we know the change in theta. And since this force is tangential to the disk, our theta in terms of where the force is to where the motion is going to be 180 degrees, so the sine of, or it's going to be 90 degrees, it's going to be perpendicular, so that the sine is just 1, and so we don't need the sine of theta term for the torque here, because it's applied perpendicularly. So we can just go ahead and plug in the variables we're given here to this equation, and once we plug these in, we can get our work. So our work will equal 48 joules. Okay, so now we need to find what is the final angular velocity. Well, when we think back to our energy unit, we knew that the work just equals the change in kinetic energy. And in this case, since this disk is only rotating, there is no linear kinetic energy to worry about. We only have to worry about this rotational kinetic energy. And so we learned what rotational kinetic energy was in the last video. So go back and watch that after this if you don't know how to do rotational kinetic energy. But we can use that to find the change in the rotational velocity. Okay? So we can first off write it as the kinetic energy final minus the kinetic energy initial. And since our initial angular velocity is 0, this just goes to 0 because there's no motion, no energy. So it's really just work equals this kinetic energy final. And so basically what the rotational kinetic energy is, and we derive this from the linear velocity one, is just the rotational inertia times the angular velocity squared, and this is final. Okay, and so now we have all these variables, so we can go ahead and rearrange this for the final angular velocity, and so we would have the square root of 2 times omega over I. And so we have all these variables, so we can go ahead and just plug them in from the problem. And so, and this should not be omega, this should be work. 2 times the work over I. And so the work is what we found in the previous part of the problem, which is 48, and the I was given at 2. And so we'll have square root of 48, which is 6.9 radians per second. And that'll be our final answer. Angular momentum is basically just momentum, but in terms of rotation. And so we can find the units of this, which will have the kilograms meters squared from the rotational inertia. And when we have this angular velocity, we know it's radians per second, but a radian is not really a unit that you use. It's more of just saying it's in terms of radians. And so you'll get this unit of, this should be kilograms, kilograms meters squared per second, which is our same as our momentum unit. Okay, and so we can actually derive this linear momentum equation in kind of a couple different ways. And the first way we'll look at it is using this Newton's second law in rotational form, where we have the torque is equal to the rotational inertia times the angular acceleration. And so we learn that angular acceleration is just the change in the rotation, or the change in the angular velocity over the change in time. And so when we multiply delta t over, you get torque change in time equals rotational inertia times this change in angular velocity. And so this is just the change in angular momentum. And you might be thinking that this kind of looks familiar from when we did impulse with force delta t, and that's because this is what we call angular impulse, which is basically just the impulse, but for angular motion, or like rotational motion. So this is just the angular impulse, which equals the change in angular momentum, just like impulse equaled the change in momentum. And so let's see how we can represent angular momentum in another way from this. And we can start from this equation. So we have, let's say, I equals I omega. And so we know that I just equals mr squared times the omega. And so we also know that the velocity equals r times omega. And so we have an r and an omega right here. So we can take one of those away and just get m times r times v, because there's 2 when you square it. But then we also know that this m times v right here is just linear momentum, mass times velocity, and these are tangential velocities. And so we can pull the linear momentum out and get the angular is the linear momentum times r. And so just like pretty much everything in rotation, the rotational version just equals the linear version times the radius. That's pretty much always what happens. And in this case, this radius would have to be at like 90 degrees. But to account when maybe you're not applying the momentum at a perfect 90 degrees, you can say r times the linear momentum times sine of theta in between. But in most cases, you'll look at where it's perpendicular to the radius, so you won't need the sine of theta term because the radius is already 90 degrees from the momentum. Okay, so let's look at an example using these angular forms of momentum. Okay, so we have a wheel with 50 rotational inertia is rotating, is what that should say, at 8 radians per second. A torque of 7 Newton meters is applied for 3 seconds. What is the angular velocity of the wheel? Okay, and so let's go ahead and list out what we have. We have the angular, rotational inertia, so 50 kilograms a meter squared. We have it's rotating initially at 8 radians per second. And a torque is applied, 7 Newton meters, for 3 seconds. So we want to know what is the final angular velocity. So that's what we're trying to find, is this final angular velocity. Should say final in there. So we can go ahead and use our equation that we learned, that we derived, as the torque change in time equals the change in linear or angular momentum. So we have our impulse equals momentum, or change in momentum. In this case, it's just the angular form. It's just like we did in momentum unit. And we can go ahead and break out what this momentum is. So we have our final minus initial. And then each one of these equals the I times its angular velocity. So final times the I times the angular initial. And so now we can go ahead and rewrite this equation to get the final angular velocity by itself, like this. Okay, and if we go ahead and rewrite this, we get that the torque times change in time plus the I omega over I. And so now we've rearranged it, we can go ahead and plug in our variables. So we have 3 seconds. And so we were given all of these, so we don't have to do anything special. We can just plug them in. And if we plug all this in, we get 8.42 radians per second. And so that'll be our final answer. And so that's how we can use this change in momentum to find the angular velocity. And so we talked about a few ways now that we can find these different angular velocities of rotating objects using either energy or momentum. So just like you can do with linear, you can pretty much do the same thing with rotation. You just have to take into account the rotational piece, which usually, if not always, comes from the radius. So let's first define this conservation of angular momentum. So just like conservation of momentum, when the momentum is conserved, the input equals the output. So this is when momentum, or in this case angular momentum, is conserved. And so when we're able to say something, the momentum is conserved, it's typically going to be when there's no external torques, just like there was no external forces when we talked about linear momentum. In this case, it's torques, which also has force in it. So when there's no external torques, I'll just say tau, which equals the force times the radius. So really, it's still the same as linear momentum, but in this case we can apply it to angular by saying torque. But if there's an external force, then there would also be a torque if it's applying to the system. So this can be used to show kind of some interesting things, like a lot of the most common example is, like, let's say you have like an ice skater, and let's say they have their hands out wide, and then they pull their hands in. And so let's say, really good pictures right here. Let's say they're spinning around and then they pull their hands in. Well, now they're going to actually start spinning around faster. And the reason for that is this conservation of momentum, because momentum is I times W, or the angular velocity. And so this is constant. The angular, this rotational inertia is constant. And since we know the momentum will be conserved if we're assuming there's no external forces, this is also going to be the same. Actually, so when they're spinning around, we can use this equation of L equals the rotational inertia times angular velocity. But we know that since momentum is conserved, this is going to be a constant. And so when they have their arms out, this is a larger rotational inertia than when their arms are moved inwards. So if the rotational inertia is going down in this case it goes down as it goes over, then this velocity must increase, and that's why you spin faster. So if you're in like a spinny chair right now, you can spin around with your arms out, especially if you have like weights or something, and then you pull your arms in, you'll start spinning faster. And that's because of conservation of angular momentum. Okay, so let's do the example where we combine all of it. So we have a 100 kilogram merry-go-round with a radius of 3.5 meters is freely rotating at a constant angular speed of 1.5 radians per second. Bob, who is a 50 kilogram runner, runs tangentially towards the merry-go-round at 4 meters per second and then jumps on it in the same direction of the rotation. What is the final angular speed of the merry-go-round and Bob? Assume the merry-go-round has this rotational inertia. Okay. So let's draw out what's happening here. So we have a merry-go-round, and it's spinning around with some initial angular velocity, and Bob is running towards this merry-go-round with some velocity and jumps onto the merry-go-round, and it keeps spinning in this direction. So we want to know what is this final angular velocity after he's jumped onto the merry-go-round. Okay, so let's go ahead and list our variables. So we have the mass, and I'll say m sub m for merry-go-round, so 120 kilograms. We have the radius of the merry-go-round is 3.5 meters. It's freely rotating, so we can assume, since it's saying it's freely rotating, there's no friction when it's rotating, so it's at a constant angular speed, which initially is 1.5 radians per second. And then we have Bob, so the mass of Bob is 50 kilograms. And he's running tangentially to the merry-go-round at 4 meters per second. So we'll say his velocity tangential is 4 meters per second. Okay, and then he jumps on in the same rotation. And we know the merry-go-round has this 1/2 mr squared relationship. Okay, so we want to know, can we even use conservation of momentum here? And the answer is yes, and that is because it's freely rotating, so there's no friction, and so we can only use it depending on how we define our system. So if we define our system as just the merry-go-round, well then when Bob jumps on it, Bob's going to apply a torque to the merry-go-round, which is going to make it not conserved. But if we just include Bob in our system here, then now we have this Bob merry-go-round system. Bob merry-go-round system. And so this system is closed and there's no external forces because it's rotating freely and Bob is just running and jumping on there. Bob is included in that system and he's moving at a constant velocity. Okay? So now we need to figure out how are we going to relate all this together to find this final speed. So let's first think about, we're trying to look at conservation of angular momentum. So we need to find both of each part. We need to find the merry-go-round's angular momentum and Bob's angular momentum. Okay? So let's think of the merry-go-round first, because this is the most straightforward. So we'll think of L naught of the merry-go-round, and I'll just abbreviate that. Okay? And so we know that the angular momentum simply equals, and we'll say not of the merry-go-round, just equals the I of the merry-go-round times this angular velocity initial, and that's what we're given. So we have defined this before, and so we can also plug in, we know this is the I of the merry-go-round, because that's what it told us it was. So we have 1/2 mass of the merry-go-round radius squared times this omega naught. Okay? And so that's our first relationship that we have. And we know these variables, so this is good. Okay, so now let's get the angular momentum of Bob. And so it might seem weird to think of Bob having an angular momentum because he doesn't have an angular momentum with respect to his own self, but he does have an angular momentum with respect to the point that the merry-go-round is spinning off of. Okay? And so instead of using this form of the momentum equation, we can actually use that the angular momentum, and we'll say of Bob, is equal to the radius times his linear momentum sine of theta. And so we learned about how we can relate angular momentum in two different ways in the last video, but we can now relate it to its linear momentum. And so we know the sine theta is going to be 0 because we were told he's running tangentially to this merry-go-round. So it's going to be perpendicular to the radius. So we don't have to worry about having him entering at some angle. So this will just go to 1. And so now we need to see what we have here. So we know the radius, because the radius is still going to be just the perpendicular radius. So if we use the radius here, then that is why we can get this 90-degree angle. But if we said I'm running out of colors here. If we said this is the radius, then we would only want the perpendicular point of the radius, which is this. So that's why we can just say r, because the radius from the center point to Bob is at an angle that's not perpendicular to where he's going to jump on. And so that perpendicular radius is what we want. And so that's why we're just using r, which was given as 3.5, because it's going to be the same radius when he's here versus when he's jumping on to the merry-go-round. Okay, and then we know linear momentum is just mass times velocity. So we have the mass of Bob times the velocity, which this is the tangential velocity, which we can just call v, or vt. Okay, so now we have the two initial momentums. Okay, so now we can actually start using the conservation of momentum. I'll just scroll down a little bit. So we already know from before that the momentum is conserved, which means that the angular momentum initial equals the angular momentum final. And so we learned before that the sum of the momentums can just be broken up into its individual pieces. And so that's exactly what we're going to do. We have the angular momentum initial of the merry-go-round plus the angular momentum initial of Bob, which equals this angular momentum final. And so this is going to be the whole system, because when Bob jumps onto the merry-go-round, now they become one system that's rotating. They're both going to have that same angular velocity, because they're not changing with respect to each other. Okay, so now we can go ahead and plug in what we just derived for these two parts, where we have 1/2 mass of m radius squared omega naught plus r mass of Bob velocity equals, so this final, so what are we going to use for final? Well, we want the whole system, so we need to add both of the rotational inertias of the merry-go-round and of Bob. And we'll talk about how we can find Bob in a second here. And then this is what we're actually solving for. And so now we're starting to get to it. We know what we're solving for at least. But we need to figure out what these equal. So I'm just going to copy down this side, and we can focus on the other side where we have to figure out what these rotational inertias equal. Okay, and so we know the rotational inertia of the merry-go-round because we were given that in the equation. But what is the rotational inertia of Bob? Well, if we think about it, Bob is acting, we can treat Bob as like a point particle at his center of mass. And as he's traveling, he's just one point of mass traveling around a point. So we can just treat that as the normal formula for rotational inertia of a point rotating around another point, which is just simply mr squared. So we don't have to have any coefficient because it's just one point of mass rotating around another point. So that'll just be the mass of Bob, the same radius as we talked about earlier, squared, times this omega final. And so now we can go ahead and cancel some things out. So we can cancel out a radius from each one of these. And we can also multiply by 2 times this so we can get rid of our fractions. And so that'll clean this up a little bit. Okay, and so that kind of cleans up this equation a little bit. And now that we've done this, we can rearrange it for this final angular velocity. So we get this whole expression here all over the other side. And so now we have all these variables are given to us, so we can go ahead and solve for this final angular velocity. Okay, so 3.5. And again, all of these were given, so we just are going to plug these in, making sure that we kept good notation on all of our variables so that we don't get mixed up between the different masses and such. See right here, this should say, this should be the mass of the merry-go-round here. So yeah, when we're dealing with these different masses and velocities, we have to make sure that we keep all the subscripts so that we don't accidentally put in the wrong mass when we're calculating our final answers. Okay, and so now if we plug all this in, we get that the final angular velocity is 1.34 radians per second. So one thing that might be a little bit confusing about this, and I actually had to go back and think about this because I was confused about it, is that why is it that even though Bob is running in the same direction that this merry-go-round is rotating and jumps on, that the final velocity is actually less than the initial velocity? Because we see it was 1.5 and now it's 1.34. And the reason for that is he has enough mass that it's increasing the moment, the rotational inertia of the whole system, that even though he's running in that same direction and applying that torque, he's increasing the moment of inertia or the rotational inertia enough so that that final velocity is actually less than the initial. And so that's kind of an interesting thing that you wouldn't necessarily expect. And so with these, it'll depend on, how much mass the person has compared to the merry-go-round, if it's going to speed up or slow down. But in this case, given the masses that we were given, it's actually going to slow it down. So that can be a little bit confusing, but that is the reason that it does that. Okay, so that's all we got for this video. Definitely leave your questions down below. I know this is a longer problem, but the idea is that you can really just take it step by step and use this conservation of momentum so that you can plug in everything that you know, and then simplify it down to get only variables that you're given, and then you can just plug everything in and get your final answer. So right here we have that when we're talking about kinetic energy, we talked about how an object, let's say that's moving in a direction, has some translational kinetic energy, and an object that is rotating also has some kinetic energy, and we called it k-rot for rotating. But if an object is doing both, then it's going to have both energies. And so as just a reminder, the rotational kinetic energy is this rotational inertia times the angular velocity squared, and the kinetic energy of translational motion is 1/2 mass times the velocity translational squared. Okay, and so when we have rolling, when we say something is rolling, we're usually going to have a situation where there's no sliding. Sometimes it could be called like perfect rolling, and this is where, let's say you have like a ball that's rolling, it's going in this direction and there's no slipping with the ground, and that means that there's no friction that's dissipating the energy. So when there's no sliding, we're going to have no dissipation of the kinetic energy for the rotational or the translational. Okay, so there'll be no dissipation due to friction. And so, yeah, but if there is sliding, then there is going to be some dissipation of this kinetic energy, and so you won't be able to relate it as conservation of energy. And so let's say we have a situation where there is no sliding, which means there's no slipping, there's no conservation of energy. We had these equations from before where like the x distance equals the r times theta, the velocity equaled the r times the angular velocity, and the acceleration equaled r times the angular acceleration. Well, when there's no sliding, we can actually just say that this is the x of the center of mass of a rolling object, and this is the velocity of the center of mass and the acceleration. And that's because at each point, we can think of it's like sticking to the ground. So if each point is rotating around with some velocity, so is the center of mass since there's no sliding. And you can kind of think of it like a gear with the ground. It can only rotate as fast as it can move across the ground if there's no sliding. But if it can spin around a bunch and not move as far, then the center of mass is not going to relate directly to these relationships that we talked about earlier. It's only if there's perfect rotation and perfect rolling without any sliding. Okay, so let's apply this to an example where we have rotation. Okay, so we have a thin hoop with a rotational inertia of mr squared and a solid cylindrical disk of 1/2 mr squared are released from rest at the top of a ramp. The objects roll without slipping down a ramp. Express each object's final velocity in terms of the height of the ramp to determine which one reaches the bottom first. Okay, so let's draw out this situation here. So we have a ramp, okay, and so we have a case where we have a solid disk that's rotating and rolling down. And then in the other situation, we have a thin hoop, which we can think of like this. Okay? And so this is also going to rotate and roll down the ramp. So now let's compare the top and bottom spots. So when it's at the top, we can call this height h naught for both of these. The velocity, v naught, is just going to equal 0 because it's released from rest in both of these cases as well. And same with the angular velocity since it's released from rest. And now when it reaches the bottom, we're going to have a height equal to 0. So we'll call our reference height like the bottom of the ramp. So that's h equals 0 at the bottom. Okay, so that's when we can say there's no potential energy because that's where we're defining our reference from. We have to define a reference somewhere. Okay, we'll also have a velocity final and an angular velocity final. So we're asked to relate the final velocities, so we'll talk about the translational velocity or the velocity of the center of mass that each one of these has. Okay, so now we can just compare them. So let's start with the cylindrical disk. So we know that we're going to have some kinetic energy initial, and this would be the disk. Okay, so we're going to have kinetic energy initial plus the potential energy initial, and this is for gravity, equals the kinetic energy final plus the gravitational final, right? And so as we talked about before, since this is rolling down the ramp, it's going to have both of these. But first of all, since it's at rest, there's going to be no initial kinetic energy for rotation or translation. And when it reaches the bottom, we define that as h equals 0, so there's going to be no potential energy final. And so we're only going to have this initial and final for the potential and kinetic. Okay, and so we can rewrite these now as we'll say our u sub gravity and the kinetic energy final, which as we talked about is the final rotational energy plus this kinetic translational energy. Okay, and so we know gravitational potential energy is just mass times gravity times height, and so this height is going to be h naught, which we'll just call h in this case. And the rotation is going to be the 1/2, and this I is going to be of the disk, so we'll say I of d. And then we have the rotational, or the angular velocity squared, plus 1/2 the mass times velocity squared. Okay, and so we're supposed to just relate this final velocity in terms of just the height of the ramp and any constants. And so to do this, something is going to need to start canceling out. So let's rewrite this. This part we already have as its final variables, but we were told what the rotational inertia of the disk was, and we see that it's 1/2 mr squared. So we can actually plug in 1/2 mr squared here, and then we will still have this angular velocity squared plus 1/2 mvf squared. Okay, and so you'll notice here the masses in this case cancel, but we still have to do something about these angular velocities and the radiuses. And so we know, since we have this rolling relationship, we learn that the velocity of the center of mass, or the translational velocity, since it's sliding, it's going to be not sliding, it's rolling, it's going to be the same thing, is just radius times this angular velocity. And so we can rewrite this as angular velocity equals the velocity over the radius. And so now we can start plugging those in. So we have GH equals, I'll combine these fractions to be 1/4 radius squared, and this is velocity over radius, and this whole thing is squared, plus 1/2 VF squared. And so this will be the final, because we're looking at the final rotational velocity as well. And so now this radius is going to cancel with this one, because this is going to be squared, but this whole thing is squared. And so we just get GH equals 1/4 VF squared plus 1/2 VF squared. And so we can go ahead and combine some terms here, and I'll just multiply by 4 to make this a little bit easier. And so if we rewrite this, if we combine our velocities and divide, we get that the velocity final squared equals 4/3 GH, and so this velocity final is going to be the square root of 4/3 GH. And so we got this without having it depend on the mass or the radius, which is important. And so this is for the cylindrical disk. Okay? And so now let's do this same process just for the hoop. So now we'll do it for the hoop. And so I'll save some time here. We know that just because it changes, we're going to get to the same point for the hoop, just with variables for the hoop, because it's still not going to have any initial kinetic or final potential, and we're just breaking these up. So I'll go ahead and start at this point, because that's where things are going to get a little bit different. So we're going to have the mass times gravity times height equals 1/2 this rotational inertia of the hoop, angular final squared, plus 1/2 mass velocity final squared. Okay, and so the main difference, really the only difference we're looking at here, is this rotational inertia. And so for the hoop, we were told, and we should really know this, is that the rotational inertia is just mass times radius squared, because it's treated as a thin hoop, right? So we just have mr squared. And we can do the same thing with this final angular velocity and just say it's the velocity over the radius squared, because it's also rotating without sliding, plus 1/2 mvf squared. And so now we'll get a bunch of things to cancel out. So the masses cancel again. These radiuses are going to cancel. And we will end up with just GH equals 1/2 V squared plus 1/2 V squared. And so this is just going to be V squared equals GH, because these two just equal 1 V squared, and then we can get our square root, and this is our final answer. And so now we can see that this is for the hoop. The hoop is going to have less velocity when it reaches the bottom, which means it's going to reach the bottom slower because it has less velocity. So the velocity final of the disk, we'll say cylindrical disk, is greater than the velocity of the hoop, which means this one's going to reach the bottom faster. And so the important relationship here is that this final velocity and the speed it gets down the ramp does not depend on radius or the mass of the object. It only depends on this rotational inertia, and which really, when we think about it, makes sense, because if we're trying to have something rotate when all the mass is closer to the center, that'll be easier to do when then rather than all the mass being far from the center. And so that's why this one takes more energy to rotate down this ramp than the one where the mass is more evenly distributed and the more mass is near the center of mass. And so that is why it'll reach the bottom faster if it's a solid sphere or if more of the mass is in the center, rather than if it's more mass far away from the object, proportional to its mass, since the total mass doesn't actually affect the speed. So that was kind of just an interesting relationship that you can derive using these rotational and translational kinetic energies. So the potential energy for gravitation is given by this formula here. Looks very similar to the force due to gravity, but this radius is not squared on the bottom. And so this is used when you have like orbiting objects or when like planetary motion, not normal like on the ground mechanics. So if we had like the Earth here or something, some planet, and maybe we had like a satellite out in space and it's, moving somewhere. It doesn't have to be orbiting, it could also be just moving away. This is where it would have this big G gravitational potential energy. And so when we look at this equation, we see that it's always going to be negative, given by this negative sign, because the masses are going to be positive, the radius is positive, this G is just a constant that's positive. So the gravitational big G potential energy is always going to be negative. And the reason for that is kind of something we can explain using the graph of what this might look like. So when we have a really small radius, this gravitational potential energy is going to be very large in the negative direction, we could say, or very, very negative. So we can start at a very negative. And as the radius gets wider, farther and farther, it's going to get closer and closer to zero. This is the zero axis right here. Okay, so as the radius approaches infinity, or like let's say you had a satellite and it shot out, as it approaches infinity, this potential energy due to the gravity of that planet is going to go to zero. And that's why it's a little different and needs to be given this negative, is because as it gets closer to there, it actually increases the potential energy. Rather than when we thought about potential energy with something on like the ground, if it was on the ground, we usually took our reference to be zero right here. But our reference in this case is like the infinity away from the planet case. And so since we took our reference to be zero, as it got farther away from the ground, it actually had more potential energy. But in this case, as the satellite gets farther and farther from a planet, you can think of it as like less energy of the planet's pulling it in, so there's less potential for it to speed up and get actually closer to that planet. And so that's why we use that convention. Okay, so let's do an example where we derive this escape speed velocity. Okay, so the escape speed velocity, what that means is kind of what this question is saying, is the equation for the minimum speed to launch a rocket to escape the planet's gravitational pull. And so we're going to assume the air resistance is negligible, so there's no external forces, so we can use that conservation of energy. And so we've learned before that the conservation energy is just the initial equals the final. So the kinetic energy plus this gravitational potential energy initial equals the kinetic energy final plus the gravitational final. Okay, so let's think about this now. Let's draw out kind of what we're talking about. So let's say we have a planet and there is some rocket ship that wants to fly away, right? So when it gets launched, it has some velocity initially, and that's what we're going to call the escape speed velocity. That's what we want to find. And we want to find this velocity so that the rocket ship gets so far away that it no longer feels any potential energy from this planet, and we want the lowest speed to do that at. So as we talked about before, as this radius between the planet and the rocket get larger, this potential energy goes to zero. And so if it escapes the planet, it escapes the gravitational pull, the gravitational potential energy is also going to go to zero. So this term is going to go to zero. But now since we want the smallest velocity that does that, we don't want this rocket ship to have any other velocity, because if it had any other velocity, then we launched it at more than we needed it to, if we want to find this minimum escape speed. And so that means this kinetic energy final also has to go to 0. So it escapes the planet's velocity or gravitational pull just enough to escape it, but not anymore to have any extra kinetic energy. Okay, so let's go ahead and we can just rewrite these variables down here, so we just know that the kinetic energy initial equals, we can subtract it so that it says minus the gravitational initial. Okay, and so now we can plug in what we have here. So we have 1/2, and so the mass here that we're going to use is the kinetic energy, so it's the mass of the rocket or the mass of the object. We'll just say, to generalize this, is the mass of the object. And the velocity is the initial velocity, which is this escape speed velocity, and that's squared. Okay, and then we just had an equation for this, but this whole thing is minus, and this is a minus g. We have the mass of the object, and we also have the mass of the planet that we're on, because we have the two masses over the radius. And so what is this radius going to be? Well, initially, before it's launched, the radius is just the radius of the planet, because it's not above the planet at all. So we can just call this radius of the planet. And so now, these mass of the objects cancel, and these negatives will cancel. So we get 1/2 escape speed velocity squared equals g mass of the planet over radius of the planet. And so now we can just rearrange our variables and get the square root of 2g mass of the planet over radius of the planet. And so that is what we can use as our escape speed. So now if all we need to know is the mass and the radius of the planet, and we can find the minimum speed to launch the rocket to escape the planet's gravitational pull, which is pretty cool. And so we're obviously making some very generalized assumptions, like the air resistance being negligible. There's no like atmosphere pushing on it. But yeah, so that's how you can derive this general equation. Alright, hopefully that was helpful. Feel free to go back and rewatch any sections as you need, or leave your questions in the comments. In the next unit, we'll start shifting gears a little bit and start talking about some oscillatory motion and harmonic motion. So make sure you stick around for that. Only 2 more units left. Thanks for watching.